Good morning, everyone. Thank you for joining me. As you know, I have talked about polynomial derivatives, followed by the chain rule. Today, the subject of our video is the discussion of the product and the quotient rules. And as you know, we are right now limited with the extent of questions we can provide in terms of examples to the polynomial derivatives. Because right now we're only learning the procedures of the chain rule, the product rule, and the quotient rule. And because I started out this whole discussion on derivatives using the polynomials, we're sticking to that. But once you've learned the three rules, the chain, the product, and the quotient, now after that we can start adding in the various different functions and then proceed from there. But the techniques of the chain, the product, and the quotient rule are applicable to any kind of function that we will discuss, whether the polynomials or anything after that. If you remember very quickly, for polynomial derivatives, we looked at the formula ax to the power of b, where the actual process of finding the derivative here was you were taking the b and you're multiplying with the coefficient of x and you're reducing the exponent by 1. And the derivative process, the d over dx, the derivative with respect to x for whatever function we were looking at, was exemplified in this manner. And you could do this individually for all the items you were trying to determine the derivative of. After this, for the polynomials, we looked at the chain rule, and the chain rule had a formula such as this: the derivative of whatever function, and we were making some sort of substitution where u was equaling to that factor which was substituted, and then you're doing a derivative, and then you're doing the du with respect to the dx to obtain the final derivative with respect to x. And you could have an unlimited number of kinks over here to this chain as needed to complete all of your substitutions and to complete all of your derivatives as needed. But today, as we're going to be talking about the product and the quotient rule, I'm going to be showing you two new templates. Those two templates will serve as the scheme or the mechanism by which you will actually carry out the product and the quotient rule. Now remember, it made logical sense to talk about the chain rule before talking about the product and quotient rule, because in questions which involve these two techniques, it's very common to see the chain rule kick in at the same time or along the process of that derivative. So it has made sense we've learned the chain rule first, because now as we talk about the product and the quotient rule, we'll see the chain rule very likely come into that type of questions. So let's look at the template and the schemes for the product and the quotient rule. When we are dealing with the product and the quotient rule, we want to be thinking of our question in terms of two functions. You could have a function f of x and you could have a function g of x. If you have a question, or your function, your general question function is something which looks like, let's just say hypothetically speaking, x squared minus 1 times sine x. And I'm not going to be talking about the derivative of this. I'm only talking about an example over here for the mechanism by which we will develop our template for doing these two rules. Or if you had a question which looks something like this, like tan x, it could be any function divided by, and we can say here, root x minus 1. You see how we have something here which looks like a product of two different functions, and then we have here which looks like a quotient of two different functions. If suppose that this right here was a function f and this right here was function g, and this right here on the top, the tan x, was the function f of x, and this right here was the denominator, the function g. Keeping this in mind, this is how we want to do our templates, because we're dealing with two functions which are combined together in your question, but separately you can identify them as two different functions: f of x, g of x, f of x, and g of x. But in one situation they're in a product relationship, in another situation they're in a quotient relationship. So as I show you the scheme or the template next, keep these f, g, and the f, g letters in your mind and see how they're related to each other in the product and the quotient form. When we're looking at the product rule, and let's just write PR over here for the product rule, your template for doing the derivative, assuming you have a question which involves two functions, f of x and g of x, is going to be like this. When you're finding the derivative of your question, which is made up of two functions, f of x and a g of x, you're going to split it up using the following scheme. You can have the g function multiplying with the derivative of the f function, and then you can have the f, and then you can have a plus in between. Then you'll have the f function, and these initial g and the f are unadulterated versions, which means you're not doing the derivative. You're only doing the derivative of that function which appears after your derivative sign. So this f, the unadulterated f function, will be multiplied with the derivative of the g function then. Look over here. If you look at this template very carefully, you'll see what I'm talking about. When you have two functions which are multiplying each other, you know you're dealing with a product rule. And remember, these type of questions, the chain rule can fall into place. But right now, we're keeping things easy. When you have to find the derivative of using the product rule, you're going to split it up in this scheme. The unedited g function will multiply with the derivative of f, followed by the sum of the unedited f function multiplying with the derivative of g. Now it would look pretty complicated, but it isn't, because if you think about it logically, it's not too hard. You have g, original g multiplying with the derivative of f plus the original f multiplying by the derivative of g. Not too hard. But now look at how the quotient rule will kick in. If you have a quotient rule, and let's just call it QR, and you're finding a derivative of your question which involves a quotient of two functions, you see f over g, this is what your template will be. You're going to have the unedited or the unadulterated original g function multiplying by the derivative of the f function. Now look, you bring a minus sign over here, then you'll have the original f function or the derived f function multiplying now with the derivative of the g function, but we're not done over here, followed by the quotient of the original g function to the power of 2. Now don't worry about how these formulas are derived. I'm not going to even go into the derivation of these formulas. We're only learning how to do the technique of derivation using the product and the quotient rule. So look at these two rules again. I went over the product rule twice verbally. Let's do the quotient rule again. If you're doing a quotient, derivative of quotient of two different functions, you're going to use the unedited g function, multiply that by the derivative of the original f function, minus the difference of the original f function with the multiplied by the derivative of the g function, all divided by the square of the original g function. Alright, when you see this in example form, it will make sense, but these are the two templates you need to learn, and if I were you, I'd commit them into memory. So our question is this: we have to find the derivative of this function. Now when we're talking about the product and the quotient rule, if you remember when I was talking about the chain rule, I was using the word composite function too frequently because we had composite functions to deal with. Here when I'm talking about the product and quotient rule, I may not be using the word composite function too frequently because we may not be seeing too many composite functions. But if supposedly a composite function were to kick in into one of these type of questions, then you know you'd be doing a product and the quotient rule in conjunction with the chain rule at the appropriate step, as that composite function would come into play. But look over here, I'm not really seeing a composite function in the true form of the sense, so we don't have to worry about it. But when I'm looking at these, I'm seeing a format of f of x multiplying by with a g of x. Imagine if f of x was this 4x squared minus 6 and g of x is this root x, then I know I have a product of two functions. So using the product formula, you know it's going to be the g multiplied by, now I'm going to simplify the formula, the derivative of f plus f multiplied by the derivative of g. See, I've simplified it. I've gotten rid of some of the extra notation, but this is what we're looking at, this formula. So if we're calling this f over here and we're calling this g, all you gotta do is plug them in and do the derivatives of those appropriate places as needed. Now look over here, g is this. So I'm going to put everything into this format right here. The derivative is going to be this. The g is just the root x. The unedited version of the g is going to come over here and you'll multiply by the derivative of the f function, which is 4x squared minus 6. And then let's bring in this positive sign, which we have to. And then we have to rewrite this because now the unedited or the non-derivative or the original f function now must multiply with the derivative of the g function, which is root x. Now it's just a simple matter of actually solving it out. Root x, you're not going to do anything with that because you're not editing it in any way, but you're doing something over here. You're doing a derivative here of a polynomial, which is easy. 2 times 4 is an 8, but the exponent is reduced by 1, so you get an 8x. The derivative of a constant is always 0. Now look over here. We're doing the original f function. You're not going to do anything with that because you're not modifying it, but we're now doing the derivative of a root x, and you know if you do these enough, you'll always get 1 over 2 root x. Anything which looks like that will simplify into 1 over 2 root x, because this is really x to the power of 1 over 2. This is really x to the power of 1 over 2. You bring the 1 over 2 onto the coefficient side and the exponent reduces by 1, you get 1 over 2 x to the power of minus 1 over 2. When you rewrite this, you look at this format right over here. Now all you have to do is open things up and you can simplify it to the greatest extent as you would want, 8x times root x will give you 8x root x, or you can do 8x to the power of 3 over 2. You can combine these, you don't have to. And then you open this up, you get 4x squared minus 6 over 2 root x. If you want to be a little more fancy, you can simplify the 2's with these even numbers here on the top. You can get 8x to the power of 3 over 2. And now I'm just opening this part over here, 8x. I'm just combining these similar bases with different exponents. You just add their exponents. And then here you get 2x squared minus 3 over root x. Now you could technically do a common denominator here, rationalize everything and do all of that, but you can even choose to stop right over here, and I choose to stop right over there. There's nothing wrong with you stopping over here, but in some books they would ask you to find a common denominator, which would be root x, and then take it to the next simplified fraction form, then combine everything and maybe rationalize the denominator out, and then you'd end up with a more suitable answer. But here we're just showing you the product rule in play, so we don't need to get too fancy with our answers, but this looks like a good answer to me. When you look at this next question, example question over here, one can say out of stubbornness that if they were to just open all of this up, multiply this with this, then this with that, using the FOIL method, just open this up into a polynomial and then do the derivative of that polynomial, they can do that and you'd still end up with the right answer as you would with using the product rule. But remember, you can get away with that stubbornness only when the questions are easy. But if supposedly you ended up putting exponents over here, then you're making it even more difficult to open and expand all of this and then go to the basic polynomial derivative technique. In those instances, then you should actually be thinking to use a product rule. In my opinion, you should be using the product, the quotient, or the chain rule wherever and whenever possible, because those are the techniques that are advocated. So when you're looking at this over here, you know you're looking at a product of two functions. This function 1, function 2, you can call this f over here and then g over here, and you know we're looking at the derivative, which will involve the product rule, and you know the product rule will be d, and then the derivative of f multiplied by the original f multiplying with g. You can see over here g is multiplying with the derivative of f plus the f multiplying with the derivative of g, and that's exactly what we have to do over here. So we'll lay it out exactly as we see it. So the derivative of this compound function would be the original g function, which is 2x cubed minus 6, multiplying by the derivative of the f function, which would be 3x to the 4 minus 7, which we have to calculate, followed by the plus sign, and then the original f function, not affected in any other way, multiplying now with the derivative of the g function, 2x cubed minus 6. Now here you have to actually just do your opening up where you can. This 2x cubed minus 6, you can't do much with it because you're not affecting it by a derivative. You're using it as a coefficient here. It's a coefficient for this derivative. So the derivative over here will be 4 multiplying by 3, which is a 12x, and then the 4 exponent being reduced by 1 to a 12x cubed. The derivative of a constant is always 0. Here this thing stays as a coefficient, you don't do much with that. 3x to the 4 minus 7. Now this will multiply with the derivative of this. 3 will multiply with the coefficient 2 to give you a 6x, but that exponent 3 is reduced by 1 to a 2. And the derivative of this constant is going to be a 0. But look over here. You can open this up some more. You can do 2x cubed times 12x cubed will give you a 24x to the 6 minus 6 times 12 is a 72x cubed. Now look over, 3x to the 4 times 6x squared will be a 18x to the 6, and then minus 7 times this 6x squared will be a minus 42x squared. Now if there are any like terms over here, you can combine them. You have a 24 and an 18. I'm a little lazy here to calculate that in my head, so let's do 24 plus 18. I get a 42. I get a 42x to the 6, a minus 72x cubed, minus 42x squared. And you can say this right here is your final answer, or if you wanted, you could isolate a coefficient number and you could isolate x squared and you can present a final answer, and maybe we can just do that. It would be a 6. You could isolate 6x squared, and then here you'd have a 7x to the 4, and here you'd have a 12x, and here you'd have a 7, and you'd be done. This right here would be your final answer in the simplified form. But again, we don't have to get too fancy over here with our simplifications because we're learning the techniques over here, the product and the quotient rule. But you can see how this has been simplified further. Let's look at an example where we will be using the quotient rule. And I will say that the quotient rule is a little bit more cumbersome only because you start bringing in that denominator where you do the square of your g function, and simply because you have a denominator involved with a square, it becomes a little more complicated. But it doesn't become hard, it just becomes a little more cumbersome. If we have a rational function and you want to call this the f of x, and you want to call this the g of x, and someone is telling you to now find the derivative of this, you could technically rationalize all of this and maybe try to simplify it, but that would be the harder way of doing it. Or eliminate the stubbornness and just learn the new quotient rule, and the quotient rule is not hard. You'll do the unedited g function multiplying by the derivative of the f function, taking the difference of the original f function multiplied by the derivative of the g function, all divided by the g function, original g function square. You have to put everything into this format, and you know what your f and g's are. It's not hard at all. Let's bring in the g function. It goes here at the very beginning, multiplied by the derivative of the f function, x squared plus 4, subtracting from the original f function, which now multiplies by the derivative of the g function, x minus 3, which all over divides by the g function square. You can see that's why I was saying it becomes a little more cumbersome, because you have a denominator now involved with a square. But that's alright. Let's start opening this up. X minus 3 on the top multiplies by the derivative of this, which you should now know is just 2x, because you're multiplying 2 with the coefficient, and the 2 exponent is being reduced by 1, so you get 2x, and you know constants are always 0 in terms of their derivatives. And now x squared plus 4 will multiply by the derivative of this. Derivative of this will just be a 1, and you know why it will be a 1, because this is x to the power of 1. 1 multiplies by the coefficient here, which is just a 1, and the 1 is reduced to 0, so you get 1x to the power of 0. You'll get 1x to the power of 0, which translates to a simple 1. 3 is nothing, it's meaningless in terms of its derivative, all over x minus 3 whole square. We'll see if you can simplify over here, and you can. You just open these things up. You'll get a 2x squared minus 6x minus x squared minus 4 over x minus 3 whole square. Now in the very last final simplification step, we're just marrying things up. The common terms are being brought together. 2x squared minus x squared is just an x squared, and minus 6x minus 4 remains as is, minus 6x minus 4 over x minus 3 whole square. And this right here represents your final answer. The derivative using the quotient rule of this function, this overall function, yields you that answer using the quotient rule. Not hard. A little more cumbersome, but not hard. Okay, we are tasked with finding the derivative of this. Now after this question, we'll start bringing in those types of questions where we have to use the combination of the chain rule with the quotient and the product rule, and you'll find out it's not that hard because you know now all three various rules. But look over here, we have the quotient of two functions, so it makes sense to use the quotient rule. You can do the original g multiplied by the derivative of f, subtract from this the original f function multiplied by the derivative of g all over g squared. This is a template or the scheme or the format we'll use for this. And here's my f right over here, and here's my g over here. So let's start. You'll have a 3x minus 4, which is your original g, multiplying by the derivative of the f function, which is root x. And the minus that, the minus from this, the original f function, and multiply to that the g function derivative, and all divided by 3x minus 4 square. So let's go to this top line over here, the numerator, and start opening it up. 3x minus 4 will multiply by, now you know, derivative of anything which looks like a root x or root u or root a is always 1 over 2 root x. You should start memorizing that because you'll see it too frequently, you might as well memorize it. X to the power of 1 over 2, you bring it over here, you get 1 over 2, x to the minus 1 over 2, and you get 1 over 2 root x. Because you can get rid of this negative exponent, bring the x down with its square root, and you get 1 over 2 root x, and you can just remember that. Minus root x times the derivative of this will be just a 3. X here, 3x derivative has an exponent of 1. You multiply 1 with this coefficient, you get a 3, and you get x to the power of 1 minus 1, you get 3x to the power of 0, which just simply which doesn't zero it out, it just converts it to a 3, because x to the power of 0 is just a 1. 1 times that 3 is just a 3. So these are some of the quick things you can look at, and never waste your time trying to determine them, because when you see them, you know exactly what it is. 3x minus 4 and then whole square. Now we have to open this up. Here you get 3x minus 4 over 2 root x minus 3 root x over 1 over 3x minus 4 whole square. Now we cannot be too lazy all the time, because sometimes we still have to do some of the steps needed to present an answer in a more suitable format. We have to do that. So we have to now create some space. Look over here on this top numerator. We have a common denominator, which is 2 root x. Common denominator of 2 root x. So let's do fraction algebra over here. 3x minus 4. 2 root x goes in 2 root x one time, so this numerator is unchanged. But this numerator over here will be changed. 1 goes in 2 root x times. When you multiply by 3 root x, you get 6x minus 6x. And this, of course, is all over 3x minus 4 whole square. Now let's finish everything over here. 3x minus 6x is a minus 3x minus 4. You can actually literally transfer this down, because this is really an over 1. When you do a fractional flip, you'll end up getting this anyways. 2 root x times 3x minus 4 whole square. Now in some areas they'll tell you to get rid of this radical over here by doing a rationalizing step. We can rationalize it. I'll rationalize it, and then I'll present you now the final answer over here. This rationalized radical, or this root x, will multiply with each of these components. You'll get a minus 3x root x minus 4 root x divided by this root x times this root x will make it just a 2x, and all times 3x minus 4 whole square. And this right here is your final answer. And I would say that this right here is a good answer. Right over here, it's a good answer. So the derivative of this rational function involving the quotient rule is right over here. So now in the rest of this video, we will make this whole topic of product and quotient rule more meaningful, in terms of we'll make the questions more realistic. They'll be realistic in the sense that we'll be dealing with the chain rule in addition to one of those product or quotient rules. And that's the type of questions which you're more likely to see. And we have to stay on topic with the topic of polynomials. Now when you're looking at this, you know we have two functions involved, an f function, f of x, or a g function, and they are in a product relationship, so we know we'll be dealing with the product rule. But when we're looking at these individual functions, we know we're also dealing with composite functions, because the f function is involved in some form of an exponent. There's some exponent, or there's some additional factor which binds these individual functions in such a way that they make them a composite function. It could have been an exponent, it could have been a radical, it could have been any other number of operators which would make the individual function look more like a composite function. So we'll have composite functions involved in both of these as we run the product rule. You know the template of the product rule. Simply, the derivative of fg is always equal to the original g multiplied by the derivative of x added to the original f multiplied by the derivative of the g function. And where and when needed, we'll be bringing in the chain rule. So we know we have an f function, we have a g function, they're composite functions. So let's actually start the derivative process. We're going to look over here, and then we'll work towards the other side. Our original g function is basically x squared minus 1 to the power of 2. Because the whole function, even though it's a composite function, it's still your g function, multiplied by the derivative of the f function. And here, you know, we're bringing in a composite function, so we'll have to do a chain rule. Then let's go to the plus, and let's write the original f function now over here. 2x plus 3 to the power of 3 multiplied by the derivative of the g function, which is x squared minus 1 to the power of 2. And these right here is exactly the composite functions. When you're dealing with the composite function derivatives, that's exactly where you will bring your chain rule into place. So let's do some substitutions over here, and I'm going to write it out over here, then we can erase it as we move. So let u equal 2x plus 3 right here. Let u equals 2x plus 3. Therefore f of u, the function with respect to u, is going to be u cubed. See, u cubed. Now look over here. Let v equal x squared minus 1. Therefore the function with respect to v is going to be v squared. Now we have the substitutions needed to actually bring in the chain rule. we'll have x squared minus 1 whole square. Now I'm just doing in the chain rule aspects. Derivative with respect to u, we have a u cube over here, and then the derivative of that function with respect to its x, the variable is 2x plus 3. Let's go back to our plus sign, which is right over here. 2x plus 3 to the power of 3, and then the derivative with respect to v, we have a v square, and you know this from our video on the chain rule. And the derivative of the v function with respect to its, actually why am I putting a u over here, with respect to its x, is going to be x squared minus 1. We have to actually calculate that, x squared minus 1. And you see the substitutions are down here. We'll have to create the space because this question is going to go down up till right there. We're going to now finish this up by opening up these derivations. X squared minus 1 whole square, the derivative of u cube is 3u squared. You know the formula, 3 comes down as a coefficient and the exponent is reduced by 1. The derivative of 2x plus 3 is just a 2. You know why? These are the shortcut ones. Anytime you see something like that, x to the power of 1, you know you're just going to, the coefficient will become your derivative. Over here, 2x plus 3 whole cube, the derivative of v squared will be just 2v. Derivative of x squared minus 1, you know, will be just 2x. Easy. Very easy. Now we have to open things up. I'm going to be looking for coefficients. I have a 2, I have a 3. Let's bring that out as a 6. Let's bring this 6 right out here at the very beginning. Times x squared minus 1 whole square. And we know we have a u square over here, but what was u substituted as? A 2x plus 3. So let's write 2x plus 3 whole square. See this 2? It comes out. The u was a 2x plus 3, but it's a u square, so it's 2x plus 3 whole square. Now let's look at these two items over here. You have a 2 times a 2 is a 4, but x can also come out with the 4. We can do 4x. And then we have 2x plus 3 by 2 over here, looking more like a reverse integral sign. So the 4x came out, then we have the 2x plus 3 whole cube, and we were left over here with just the v value, v. And the v value was x squared minus 1. That's what the v value represented, was a substitution. V was equal to x squared minus 1. Now look over here. We can look for common terms over here and then isolate. If you're looking at 6 and a 4x, you can isolate a 2. Now let's look at x squared minus 1 whole square and x squared minus 1 to the power of 1. We can isolate x squared minus 1 to that power of 1. Let's look at 2x plus 3 whole square and 2x plus 3 whole cube. We can isolate the 2x plus 3 whole square. Now, this entire item goes in all of this. How many times? Well, it certainly goes into the 6 3 times. X squared minus 1 goes in x squared minus 1 whole square. A single x squared minus 1 times. This whole item right over here goes in how much over here in terms of that expression? It goes in, well, we still have that plus sign we have to bring out. 2 goes in 4x, 2x times. X squared minus 1 goes in x squared minus 1 times. 2x plus 3 whole square goes in this whole cube. 2x plus 3 times. Now we have a task nearing completion by simplifying what's in the square brackets. Open it up. 3x squared minus 3 plus 4x squared plus 6. Let's bring that out here. 3x squared minus 3 plus 4x squared plus 6x. We're looking at this and we're going to bring it all out over here. Simplify. 3x squared plus 4x squared is 7x squared plus 6x minus 3, and I believe we should be done. We should be done with this question. So this question over here, which was a product of two composite functions, when you derived it, you obtained this derivative here. And of course, if you had a good point on this curve, on this original curve, you would plug in that x coordinate in these areas of x's and you'd get a numerical answer. And that numerical answer would represent your slope of the tangent line, the instantaneous rate of change at that specific point, and from that you could also determine the equation of the tangent line. But it looks like a good answer, and you can see how composite functions affect drastically the product rule by making it more complicated but not hard. It makes it more complicated but not hard. We'll be looking at some more of these examples coming up next. And here lies before us an interesting question. You know, we have a rational function here which will involve the quotient rule, but we also have a composite function here in the denominator. So we'll have a quotient rule kicking in along with a chain rule. And you know the quotient rule is simple. The original g function multiplied by the derivative of the f, and then you minus f original function multiplied by the derivative of the g function all over g squared. And you know the chain rule already. This right here is our composite function, so we have to use, when we get to the derivative of this part, we'll be using the chain rule along with that. And this is how everything is going to play out. This right here is my f function right over here, and this right here is my g function over here, and we just lay it out. Let's do the original g function, x squared plus 4, and then we'll do the derivative of the f function, which is x to the power of 4, not too hard, minus, we write here the original f function multiplied by the derivative of the g function, x squared plus 4, all divided by the square of the g function, x squared plus 4. If you look at it, x squared plus 4 is really to the power of 1 over 2, and if we make this to the power of 2, we eliminate the exponents and we just get left with x squared plus 4, which is good. It actually helps us out. So we lose a radical over here, which is good news. Now when we actually open things up, we'll bring the chain rule over here. But let's go to the next step. X squared plus 4 times the derivative of x to the 4th, will be 4x cubed. Easy. Minus x to the 4. Now we have to bring the chain rule over here because this is a composite function. Let u equals x squared plus 4. F of u is equal to root u. So look where derivative with respect to u, root u, and then the derivative with respect to x squared plus 4 over x squared plus 4. Now I've done the derivative here. I just have to now finish this part over here. I'll have 4x cubed multiplying here with this as a coefficient, x squared plus 4. I've done nothing over here other than just write the coefficient first and the radical next. And then I have x to the power of 4 multiplying by, anytime you see this, you're always thinking about 1 over 2 root and whatever the variable is. I was going to put an x over here, but it's a variable of u. 1 over 2 root u. And the derivative of x squared plus 4 will just be a 2x. Everything here on the bottom remains unchanged, x squared plus 4. Now in the next step, we'll carry and simplify what we can. And we don't have to take this to the extreme level. We're just showing you how you combine these things together. I'm going to rewrite everything. Actually, before I rewrite everything, I can take this 2 and I can cross it out with this 2, because here these 2's will cancel out. And let's start writing everything over here. We'll have 4x cubed square root of x squared plus 4 minus x to the 4th times that x is an x to the 5. X to the 5 over root u. But what exactly was u? It was x squared plus 4, wasn't it? The substitution, x squared plus 4 all over x squared plus 4. Now if you want to be fancy, we can do common denominators and we can actually take it to that level. 1 goes in this, x squared plus 4, root x squared plus 4 times, we'll multiply with that, you get 4x cubed times x squared plus 4 minus x to the 5 all over this root x squared plus 4. Root x squared plus 4 can actually be attached with the denominator over here, because when you flip everything around, this x squared plus 4 will multiply by this root x squared plus 4, and you really get x squared plus 4 to the power of 3 over 2. Remember, this is all algebra part. You can verify this alone on your side. If you want to take everything to the last step, it would involve the opening of all of this. 4x cubed times x squared would be a 4x to the power of 5. Minus from that, x to the power of 5 would be 3x to the power of 5. 4x cubed times this 4 would be a 16x cubed plus 16x cubed, and you'd have your final denominator here, x squared plus 4 to the power of 3 over 2, and we're done. These type of questions can be a little long, but not in the derivative part, but in the simplifying part where you actually have to present a proper answer. That part can become a little more involved. How about we look at this question next? And the combinations are endless. The questions can get very complicated, but we have to stay within the realms of practicality. We don't need to make the question so confoundingly large and confusing or so elaborate that it loses the practical significance, because the real life models are not entirely absurd in terms of their appearance. They have to have some sort of logical functions to them. So let's look at this, and we have to find the derivative of this. We know we have a function here on the top, the f function over here, and we know we have a g function here, and we know we have to use the quotient rule, but we also know that we have a composite function, that the g function, the g of x, is a composite function. So we'll use the quotient rule in conjunction with the chain rule. So let's just lay it out. We now know in our heads what the template is. It'll be the g function, original g function, multiplying by the derivative of the the derivative of the f function, minus the original f function multiplying now with the derivative of the g function, all over the original g function but squared. If this is 1 minus x squared, when you square it again, it becomes 1 minus x to the power of 4. Here is our step where the substitution must kick in. Let u equals 1 minus x, therefore f of u is equal to u squared, because it's u squared, right? So let's do the chain rule now in the next step. 1 minus x whole square d over dx, x over here minus x times d over du, derivative of this function with respect to u square, and then the derivative of that same function with respect to its x variable, 1 minus x, all over 1 minus x to the power 4. And sometimes these questions are actually easy. Imagine if you had a 1 over here or a constant over here, and then where are you're bringing in the derivative of that constant. Like if suppose if this was a 1 over here or a 2, and you have to find the derivative of 2, which you know to be 0, it would zero everything out and your question would automatically become easy. You would lose this entire part over here and you'd just be dealing with that part. But let's continue with this question. You'll have 1 minus x squared, derivative of x is just a 1. It's just a 1 because x is to the power of 1. When you bring it over here, you get 1x to the power of 0, which makes it just 1x to the power of 0, or just 1. I was repeating what I was saying there. It makes it just 1. Now look over here, minus x times derivative of u squared is 2u. The derivative of 1 minus x would be just a minus 1. Why? Because it's minus x to the power of 1. This 1 over is meaningless because it became a 0. It became a 0 minus x in terms of its derivative. Anyhow, you have a minus x, 1 multiplies with this, you get a minus 1x to the power of 0, and you get a minus 1. Hence, you have a minus 1 over here. These are all things, as you do derivatives, you'll do them right away. The minute you see something like that, you'll think it's just minus 1. All over 1 minus x to the power of 4. Now let's come up over here. And we have to plug in and modify this area over here. So now that we've come up to this part, let's just finish it up right over here. I'll combine and make some modifications here in my next step. I'll have 1 minus x square. This minus will multiply with this minus, become a positive, and then I have a 2 and an x, so it'll become a plus 2x multiplied by u, which is just 1 minus x, over 1 minus x to the power of 4. Sometimes you can do these questions so many times in your head that you get these tongue twisters or tongue teasers in your head, and you're saying one thing and you're writing another thing, or you're just misstating the words, and it just happens. It's like an involuntary event. These type of terms are just talking them out loud can bring in a lot of tongue twisters in your mouth. Anyhow, let's open up this 1 minus x square, then you'll get plus 2x minus 2x square over 1 minus x to the power of 4. If you wanted to be fancy, you could open up this entire numerator, combine the common terms, and present a final answer, but I won't take it to that level because I'm basically just 1 or 2 levels away from a very good final answer. But we'll stop right over here because you just have to expand this numerator, combine the common terms, and rewrite everything with this as your denominator, because the denominator will not change any further. But this right here is a good answer over here in terms of the purposes for showing you this quotient rule along with the chain rule. I want to present 2 more examples before we end this video. If you look at this question over here, this is just nothing that I'm going to take to completion as my last 2 questions. This is like a quick trick I want to show you only before I do your final last 2 questions. When you see something like this, don't make the naive mistake. I hate to say that, but don't make that type of mistake by saying this is your f and this right here is your g, and you want to now apply the product rule along with the chain rule, because look what happens if you do that. If you apply the product rule, you do x plus 1 whole square, which is your g, multiplying by the derivative of the f function, which is just a plane 4, plus the plane 4 multiplying by now the derivative of the g function, x plus 1 whole square. And now you know you have to do the chain rule over here. And you know all of this will zero out because the derivative of 4 is just a 0. This will zero out, and look over here, you'll end up with having 4 times the d over du, and then this right here by substitution will become a u square, and then you do your chain rule over here, you get x plus 1. The point I'm trying to make, there's no point in you viewing this in terms of the product rule. You don't need to, because simply here your one function is just a constant. A better way to have viewed all of this was, when you're looking at this step over here, rewrite it as 4 times the derivative of x plus 1 whole square. And then if you proceed with this, not using the product rule at all, just go directly to the chain rule, you'll end up with exactly what you're seeing over here, aren't you, right? The 4 got left or pushed aside, like here it's pushed aside, but you're doing the derivative using the chain rule of whatever is afterwards. So don't waste your time doing the chain rule from the beginning when you have a situation like this. And likewise, I can give you another similar example where you have the quotient rule or a quotient type question where you can just skip the quotient rule entirely, and you can go directly to the point that I'm trying to make. If supposedly your question was x plus 1 whole square now divided by 4, you could say this is your f function, this right here is your g function, and then you can go through the elaborate process of doing the quotient rule, x plus 1 whole square, and you know the chain rule will come right over here because we're doing a derivative here of a composite function. And then you'll do x plus 1 whole square derivative of this 4, which you know will zero out, and then you'll have 4 square over here. You don't need to go over here because it's going to zero out over here anyways. What you can do over here with this type of question is bring your 4 out. Bring it out as this 1 over 4 now derivative with respect to x plus 1 whole square, and you can calculate and you can take this to the end. The only reason why this thing will give you the same answer as this answer over here, because you see this 4 over here and you see the 16, this would become a 16, right? When you simplify this out at the end, you'll still get your 1 over 4, and here you're still getting your 1 over 4, so it'll work out. So be confident in these type of shortcuts you can take. So when you have as one function a constant entirely, don't use a quotient rule, or don't use a product rule, and don't use a quotient rule. Bring your constant outside of your derivative as a coefficient and do everything else, and then bring that back in at the end. You see, you can bring it back in at the end, and while you've done the derivative of everything else, and you'll still get the right answer. So keep that in mind. These coefficients can be viewed as non-functions and just be brought out. These constants, I mean, you can view these constants as coefficients of your derivative. So when I'm tasked with finding the derivative of this, in keeping with what I just said, I'm going to do exactly what I just said. I'm going to bring this out over here, and I'm going to view this as 2 times the derivative of x squared times 1 minus x. Now, of course, I'm still looking at the product rule, and I'll still be dealing with the chain rule, but that's fine. At least we push the 2 aside. You don't have to, but you can. So let's look over here. Here's my f and here's my g. So I'm going to do 2 times the original g function times the derivative of the f function plus the f function multiplied by the derivative of the g function, 1 minus x cubed, and you know the 2 is still sitting outside. 1 minus x whole cube times the derivative of x squared, which is just a 2x, you know how to do that now, plus x squared. Do a chain rule substitution, let u equals 1 minus x, so f of u is equal to u cube, d over du, u cube, and du to dx, 1 minus x. Let's take this to the next step. You'll have 1 minus x whole cube multiplying by this 2x, nothing has been done already because the derivative is already done, plus x squared times 3u squared times 1 minus x is just a minus 1, the derivative of 1 minus x is a minus 1. All we gotta do is combine terms. You can just bring the 2x as a coefficient of this 1 minus x cubed, 1 minus x whole cube plus minus 1 times 3 times x squared is in minus 3x squared, minus 3x squared. Minus 3x squared times u squared. Let's resubstitute what u was, 1 minus x whole square, 1 minus x whole square. Now look over here. We can bring out common terms. The common terms we can bring out are x's and 1 minus x. Look, 2 times, I'm bringing out an x and a 1 minus x. Between these two, the common term is 1 minus x whole square. This goes in here 2 into 1 minus x times, and this goes in all of this, minus 3x times. Okay? Open up the parentheses and bring the 2 back in. You'll get 2x times 1 minus x whole square. You'll get a 2 minus 2x. You'll get a 2 minus 2x minus 3x. So I'm going to do that all in one step. 2 minus 5x, and we are done. Our question is done. Not too hard, but I pushed the 2 aside. You didn't have to. You could have treated this all as an f. Your f function, you could have treated this all as your g function, and then the 2 would just play along in here, and you'd still get the same result. So this is this one question completed. We will end our video today with this example. Just by looking at this, we have a composite function here in f. We have a composite function here in g. The f of x and g of x are both composite functions, so we're going to be using the quotient rule and we'll be using the chain rule. So that only thing that remains at the end is just the basic algebra. So let's look over here. You know the formula for this will be just the g multiplied by the derivative of x of f, derivative with respect to x of f, minus f multiplied by the derivative with respect to x of g all over g squared. And you know the chain rule will kick in at the appropriate steps. So let's do that. Our g function will be x squared minus 3 whole square multiplied by the derivative of the f function minus the f function multiplying now with the derivative. Well, we're not calculating the derivative, but we're laying it out, multiplying by what will eventually be the derivative of the x of the g function, which you know is x squared minus 3 to the power of 2 divided by the g function x squared minus 3 whole square, so it becomes to the power of 4. Now in the next step, we're going to do our substitutions in the chain rule, and you should now be able to do the chain rule in your head. Let u equals 5 minus x, and then f of u is root u. Let v equals x squared minus 3, f of v is equal to v squared. So we do all of that in our head. So x squared minus 3 whole square times derivative with respect to u, that'll be a root u, and then the derivative of u with respect to x will be 5 minus x. Remember, we are limited here in terms of our space. This is your original g function, f function, which is right over here, which I'm putting here now, multiplied by. Now the derivative with respect to v will be just v squared, because I substituted x squared minus 3 for v, so it's v squared. And the derivative with respect to x for that v function will be x squared minus 3 all over x squared minus 3 to the power of 4. Now let's open things up. We'll have, come over here, x squared minus 3 whole square. Root u derivative will be 1 over 2 root u. You can see that, and you've seen that come too frequently, that this should be something memorized. Any variable with the square root, the derivative of that is 1 over 2 to the same variable, square root. The derivative of 5 minus x will just be a minus 1. Minus root 5 minus x. This derivative right here is a 2v. Derivative of this will be just a 2x. Remember, derivatives, the simple derivatives are following this format. Ax to the b becomes ba x to the power of b minus 1. That's all I'm doing for these individual derivatives. This will be all over x squared minus 3 to the power of 4. All over x squared minus 3 to the power of 4. Now, if you want it, and that's what I want to do, is combine these common terms. And for that, we're going to come down right here to the very end of the board, and we'll finish it. And let's make some space. Let's eliminate this entire denominator over here. Imagine all of this right here was dividing by our denominator, which we know was x squared minus 3 to the power of 4. So let's write all of this over here again properly. You'll have a minus 1 over 2, minus 1 over 2, and our u here is 5 minus x, and you know the numerator we have x squared minus 3 squared, right? Now let's look over here. 2 times 2 is a 4, and there's an x. Minus 4x, you have a root 5 minus x, and then the v represented what? What did our v represent? X squared minus 3, right? X squared minus 3. This is all over 1, and then this all is over our original denominator, x squared minus 3 to the power of 4. You could do common denominator over here and work it all out and then present a final answer. I won't do that. We'll just stop right over here. But you can see that this question involved the quotient rule and involved the chain rule, and it requires a good amount of space to finish it out. A good amount of space. So pretty much, I'm going to stop with this question right over here. So we've talked about the chain rule, we've talked about the polynomial derivatives, which follow this scheme over here. We've talked about the product rule, and we've talked about the quotient rule, and you see how these rules intermingle with one another based on the original function that you're dealing with. It can get pretty complicated, or it can be pretty easy. It depends on the type of question you're given. But pretty much you have the format in front of you. Keep in mind the chain rule, the product rule, and the quotient rule, and the derivatives of the basic polynomials. Now all that remains is to start bringing in different types of functions so we can learn how to do the derivatives of those various functions. You can't just be sticking to polynomials only. We have to talk about trigonometric functions, hyperbolic functions, the various other kinds of functions and their derivatives. And the chain rule, the product rule, and the quotient rule will come in with all of those types of questions. I hope you enjoyed this video. I hope it wasn't too confusing, but please keep tuned. I'll have many more videos coming up. Have a nice day. Bye.